Okay, so this video will be the distribution of the sample mean. We have some terminology to get through first before we get into calculation. So, but once we put some numbers on it, it will look better and sound better. The sampling distribution of a statistic is a probability distribution for all possible values of a statistic computed from a sample size n. The sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the random variable x bar computed from a sample size n from a population with mean mu and standard deviation sigma. Now suppose that a simple random sample size n is drawn from a population with mean mu and standard deviation sigma. The sampling distribution of x bar has the relationship of being equal to the population mean. So the mean of your sampling distribution is going to be equal to the population mean. And the standard deviation of your sampling distribution is going to be equal to the population standard deviation over the square root of your sample size, square root of n. Now the standard deviation of the sampling distribution of x bar is also called the standard error of the mean. Now, if a random variable x is normally distributed, the sampling distribution of the sample mean x bar is normally distributed. So now that's very important because that allows us to be able to use z-scores in the z-score application. You have to have that normal distribution relationship. So the IQ, we're going to be calling x of humans, is approximately normally distributed with mean 100 and standard deviation 15. Compute the probability that the simple random sample size of 10 results in a sample mean greater than 110. So let's start off with our givens. The population mean is 100, population standard deviation 15, sample size n is going to be 10, and the sample size mean in question is going to be 110, sampling distribution mean. Now the relationship of our sampling distribution mean is going to be equal to the population mean, which is going to be 100. Standard deviation is going to be sigma over the square root of n, so that's 15 over the square root of 10, which is 4.743. So now we can use that in order to find our z-score. So we take the x bar minus mean x bar, mean sub x bar over sigma sub x bar. So these are notations for our numbers. So it's 110 minus 100 over 4.743. That'll give us 2.11. Now we can go to the z-score chart. When we go to the chart, our chart value will give us 0.9826. Remember, the chart that we use will always give us less than. We want to know greater than. So if we want to know greater than, we take that less than value, subtract it from 1. Remember, greater than with the chart value that we have, we subtract that from 1, and that'll give us 0.0174. So the probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is 0.0174. All right. Central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So we increase the sample size, we can get approximately normal distribution, no matter what the population distribution is. And that's very key because once again, we need a normal distribution in order to be able to use our z-score application. If the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. So 30 is the magic number. We want to go over 30, be equal to 30 or go over 30 in order for our sample size to be approximately normally distributed. So let's look at this next example. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. So it's not normally distributed, it's skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines that their mean weight gain during the pregnancy is 36.2 pounds. Does this result suggest anything unusual? So once again, we start off with what we know or what is given. Mean population mean is 30. Standard deviation is 12.9. Our sample size is 35. So now since it's 35, even though our population is skewed right, a population distribution is skewed right according to the central limit theorem. And our marker, we have a sample size that's over 30, and so that means it's going to be normally distributed, and we can use our z-scores. Then x bar is going to be 36.2, the sample size mean in question, or the sample mean in question. Um, our mean X sub x bar is going to be equal to the mean of the population, which is going to be 30. Standard deviation sub x bar, or the sampling distribution of both the mean and the standard deviation, is going to be the population standard deviation over the square root of n, which is going to be 12.9 over the square root of 35. That'll give us 2.180498. Now plug that into the z-score relationship. That'll be 36.2 minus 30 over 2.180498. That'll give us 2.84. Go to the z-score chart. The z-score chart gives us 0.9977, which represents less than, once again. Now, since we want to know how unusual this is, then we're going to, we want to know the chance of it being greater than, or the chance of getting something greater than what we have. So once again, we're going to do greater than, we'll do 1 minus 0.9977, which gives us 0.0023. So this is going to be unusual, an unusual occurrence, because the probability is less than 5%. Let me know if you have any questions.